This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good morning, everyone. We continue with the lectures, and the third workshop is this week, starts this week, ends next week. It's a shorter one. The report will be due Sunday evening next week after you finish, so the report will be immediately due. There won't be much of an extension there. Then the fourth workshop will be also a short one, mostly project-based, and then it will end at the end of the semester, and last week we will also have a workshop. So, and then the deadline will be end of the weekend that week, last week, because I'm not allowed to put deadlines to the SWOT-WAC. There is a regulation. So, and then we will be done with the workshops. And the last, so I will cover today the rest of the support vector machines, and then a little bit of performance evaluation metrics that you have already used, and it was in the slides. I will go over them and then start with the deep learning, neural networks and deep learning. Okay, we were talking about kernel trick, so this is, I think, the most explanatory slide. It's a bit of a mysterious looking thing, but in reality, what we do with the kernel trick is take the data points on the right-hand side and then transform them to a different space, right, with a nonlinear transform phi of x. But this is what we have been doing in the linear models. The whole trick here is if you choose a good transform, things that may require a nonlinear boundary to separate for this classification problem, for example, in the higher dimensional space, you may use a simpler separator, separating hyperplane. And the other aspect of the trick is you don't need to even sometimes know the transform itself, but all you need to know is the dot product of the transformed vectors, and that's what the kernel function gives us. So it gives us a way to compute the dot product, and as we have discussed, that is sufficient. To highlight the fact that things are not always linearly separable, that is important because if you don't take that transform, your separating hyperplane is just a wx plus some omega 0 or wx plus b. And then if you're on the right-hand side of it is greater than 0, less than 0, and if you're on top of it, it's equal to 0, right? And this is a nice question, I believe, because it shows that some things are not linearly separable. Then you need to do something else, and sometimes things are not even non-linearly separable. We will also discuss this next. So let's look at this. I like these two pictures essentially. On the left-hand side, right? So you cannot find a nice red separator like this, right? Separating hyperplane. On the right-hand side, though, like if your point clouds belonging to the two separate classes are sufficiently, far from each other, then you can actually have a linear separating hyperplane. So how do we mathematically express that? We have a given set of data points, xn, and we can actually define the convex hull of the set of all points x as this, and then we can also define, as shown in the pictures, the convex hull of each class separately, right? So in this case, by definition, alpha n's need to be non-negative and then need to add up to 1. Then you get all the points spanned by these convex hulls, right? So for the blue points and the black points, I can have alpha n's and beta m's, for example. Right? The second set of points will be then the blue ones, and then I can define the convex hull. So here, this is a bit flawed picture, so it is not a proper convex hull here. Ignore it for now. Like assume that there are points in the corners. All right, so on the right-hand side. So and how do we define linearly separable? This is very important at the core of classification, right? We have two sets of points. They are linearly separable if there exists a vector and a scalar such that we can define this hyperplane, right? And then Hyperplane means like plane in the 3 dimensions. It's a line is shown in 2 dimensions, and in higher dimensions, it's whatever dimension d is, your hyperplane will have d minus 1 dimension, right? To separate it into 2 pieces for binary classification. So essentially, if you're on one side, it is positive. If you're on the other side, it's negative. And as I said, if you're equal to 0, you're smack in the middle. So the question asks us if the convex hulls intersect, right? The 2 sets of points cannot be linearly separable, and conversely, if they are linearly separable, they do not intersect. So this is the visual proof, right? In the mid-semester test, I asked you a visual argument because like I didn't want to go deep into turn it into a formal mathematics class. So if I had asked show a visual argument, that would be a visual argument, right? And then the mathematical version of it is now we will see a bit more formal version. That's still not terribly formal, but still a bit more formal than drawing a picture. Is I will just, in the interest of time, not spend too much time, and then show you the argument here. Maybe we can make it bigger. So we will show by contradiction, right? It's one of the main proof methods. So what do we see here? So we have the I have deleted it. Okay. Give me a sec. Yeah, let's go over. What did I do? Okay. So we have the convex hulls of xn and yn. These are the class 1 and 2, right? Class 1 and class 2, and it's a binary classification problem. Let's make it crystal clear. Right? So we want to separate these 2 sets of points. Dog pictures, cat pictures, I keep saying that. If there is a point z such that it belongs to both of them, right, then the z will be smack in the middle, right? So z is here. Then I can write it into, it is supposed to be within the convex hull of one and the other as well, right? So I can write it as an alpha n xn, but also I can write it as beta m x yn. And then the number of points may be different from each other. So alpha and beta, they have the same property. By the definition of a convex hull, they add up to 1. So if these were linearly separable, then we can write the separating hyperplane. So some w hat times z, dot product z, plus that would give a scalar. Omega z is a scalar. Then I can substitute z here with the x's. So I get this plus omega 0. And the fact that sum of alpha n equals 1 means I also can bring it omega 0 inside. So I can do this parenthesis because alpha n's are non-negative and sum to 1. So that motivates this part. All right? So once I do this, we know that if they are linearly separable, then we will have each of the alphas are positive. This is positive, so essentially this is positive by assumption, right? And then alpha n's are positive, non-negative. So you sum up a bunch of non-negative numbers, you cannot get negative, so you get greater than 0, right? So then if I write z in terms of x, then I get this. But if I write z in terms of the other betas and y's, then I need to be on the other side, right? So these are now all negative by the assumption, and then because we assume it's linearly separable and intersecting, but these are positive, non-negative, so I end up with a negative result. So that is a contradiction. Therefore, they cannot be linearly separable if the convex hulls are intersecting. That's one direction. And the other direction is if they are linearly separable and there's a point in the intersection of the convex hulls. Actually, it's the same analysis, but you make the argument from the other side. So that also is a contradiction. So everything is contradicting each other. So you cannot have this. Therefore, we have shown that the 2 sets of points cannot be linearly separable, and conversely, if they are linearly separable, they cannot. The convex hulls shouldn't intersect. very intuitive. The proof is extremely simple. Sometimes these proofs are you know, logically, you want to make it airtight, right? So they seem complicated because of their simplicity, because you're making a very intuitively obvious argument, but you do it in a logically very airtight way. So that is important. So then what do we do? Essentially, there is also this issue of when you are not linearly separable, what you do is you do the kernel trick and use a nonlinear kernel to map the data points to a space. Where's my mouse? Ah, okay, here. You map them to a space where with phi of x, and then the kernel function, which gives me again the dot product in that space, and I deal with that through this, right? So I've got this whole story of mapping. Now, just to remember, this is the main formulation essentially. So I try to minimize the margin such that we have discussed, we can write it with these constraints so that everything is far away, and then we try to maximize the margin. Maximizing the margin, because margin is 1 over w, that is same as minimizing w. Right? And then I have the Lagrange multipliers, and most of the time we use the dual formulation. I will come to that, where alpha n's are the Lagrange multipliers, which tells you which, and if they are positive, that those are the points that are the support vectors, which play an active role in drawing the boundary, and those points which have the lambdas, alpha a's, which are the Lagrange multipliers that are 0, they don't play a role in drawing the, defining the boundary, and the hyperplane, hyper surface in this case, because it's nonlinear, and then that's the story. So when we write the y, they are written in terms of the ANs, and as I say, this sum is over all the points, but a lot of points hopefully zero out. Actually, it's ideal that if I can define the boundary discriminant with fewest number of data points, that's a bit more desirable than many data points playing a role in drawing this. All right. So another, and then here, as we said, the kernel as defined in the previous kernel function in terms of the dot product of these transforms. So that product between x and x prime now is in the transformed space. Therefore, it's phi of x and phi of x prime, and that's a dot product of these vectors, right? Okay. So therefore, all I need is this k, the kernel function, and I can define different kernels. You have done this in the workshop. Actually, you have also drawn the linear kernel in the workshop, and you have now the nonlinear kernel in the workshop. So this should be all, you have played with it on hand, right? So this is the explanation. Another way of thinking about, it's a bit of a mysterious process, right? I keep saying you are transforming it to a space, but then it makes it is known that it is a transform to a higher dimensional space, then things are made separable as illustrated in these nice figures. But, especially for the most commonly known RBF kernel, can we a little bit get more insight to this? And I put this question, this is not something I ask you to derive, but I wanted to show you, mathematically. So if I'm giving the RBF kernel, what is the phi of x? It's not obvious, right? K of x, x prime is phi of x dot phi of x prime. But I'm not given phi of x, and it is, why does this RBF kernel work for many problems? It's a mysterious question. And I have put these nice links here about a paper, and there's a nice video, but there's also this question itself. Actually, one can show that the RBF kernel maps the input x to an infinite dimensional space. That's interesting. And one shows this through the Taylor series expansion. That is, I will show it now. And it hopefully demystifies a little bit of how these kernels work. So let's really look at this. So that's the k. That's very much of a Gaussian, right, between x and x prime. Let's ignore for now the simple version. Let's consider the simple version where we don't have we have a simple variance as a scalar, right? Identity, and then I will even more simplify, making sigma 1 to make the derivation a bit cleaner. So if we write this Taylor series expansion, this is a bit of an algebra and analysis. It turns out we have such an expression. So we have the exponential terms, and we have this dot product, and we have this infinite sum, right? It's a series. So when we set the sigma equals 1, actually things get a bit, as we've done here, things get a bit cleaner to explain. And if you separate the terms a little bit, this is complicated because the terms are really very much interleaved. But after multiple steps here, as I said, I don't expect you to derive this, right? But just to have a look, so you can see that we have this term and this term, a term in terms of x's and a term in terms of y's emerge. And as we know, kxx prime then, or xy in this case, will be phi of x and phi of y dot product of the two. And the sums are defining the dot product. And from here, we can see the entries of the future map are this. So that is a bit of a infinite sum, actually. And the individual elements are these individual entries. So you have done infinitely many of these entries with the monomials. I think they're part of these individual elements of this polynomial. So you can see that by using the simple RBF kernel, actually I am doing a pretty complicated infinite dimensional transform. I take my x and throw it to an infinite dimensional space. Why do I do that? If I throw it, intuition is as I showed in the picture, if I throw it to an infinite dimensional space, it becomes quite separable. X becomes more separable than y. And that's an interesting thing, that's the interesting insight why it, is so powerful and so commonly used. All right? So I go from linear kernel to linear case, linear line. When things are not linearly separable, then I try to draw a nonlinear line, and then this nonlinear function is a discriminant from the hyperplane to a hypersurface, nonlinear hypersurface. But sometimes even that is not sufficient. And that's the next step. Or any questions on this? Yes?
So with the previous slide with the parabola?
Yeah, that's just the representative, yeah.
Is that from 2D to 3D?
Yeah, that's a 2D to 3D. This would be then whatever d to infinite. Right? So that 2D to 3D is only nice because it gives an intuition, right? It's a kind of a sketch. It shows that if you go one dimension up, things may suddenly become separable. And if you continue the same line of thinking, if you go from a finite dimension to a higher dimension or finite dimension to infinite dimension, things will become also more and more separable. That's kind of the thinking. Yep, thanks for good question. All right, any other? You're with me, right? So this is how things work in the background. You did it yourself in the workshop. As I said, there is one more step, and because in real life I mentioned I've now motivated this nonlinear function that is separating, right? And if you have done the workshop, you could have maybe drawn this boundary, and then these green ones, they are the support vectors. Those are the support vectors that have the data points that have a positive. And all other data points, A is 0. Right? And they define, but it's also obvious, right? They define the boundary. They are closer to the boundary. This is also defining the boundary. So it's not necessarily next to the boundary, but they separate the blue crosses from the red ones. But, this is, machine learning is very real life. It's not just a theory where you just do nice theoretical results. The reason why it is so popular is it's been from the get-go dealing with real data. And real data is messy and, And because real life is messy and processes are not that simple. You know, the real life processes are not done for the sake of doing final exam questions. So that's why I hate this whole final exam thing. People come to me and say, what is going to happen in final exam? Who cares? Like, I mean, you will not have a final exam after you graduate. When you go to a job, will your boss ask you to do a final exam? I'm really curious, right? Has anyone ever done that, encountered that? So you will see a lot of messy things, and you're supposed to find your way. So the messy thing is, what if the points are on the other side? You still need to separate the classes, right? So if the training data points are not linearly separable, even in the future space, or I shouldn't say maybe linearly, they are not separable. Let's edit this as we go, because it may give the wrong impression. They are not separable, even in the future space, right? Even after the kernel trick, you do your best. What do we do? I mean, we do our best, and then what we do is we introduce these slack variables, psi n greater than or equal to 0, to handle the points that are violating the margins. It is shown in this nice picture here. I think it's really nice. So you see these points are on the margin. Blue lines are in the margin. I show it in the linear case because it's easier to show. Red one is our separating hyperplane. The same holds for the nonlinear version. But you see there are these, these bluish points that are crossing the boundary, or these yellowish points that are on the, and this one doesn't cross the boundary, but it is within the margin, right? So those are violating my boundary, because there are indeed noisy data and messy data. You cannot draw a perfect line, even nonlinear line, separating everything perfectly. There will be some points we will be crossing. So what do? We need to kind of take this into account. And how do I do it? Original constraint was, for these nice points, I could write it Tn, Yn greater than or equal to 1, because I could scale things. Now I need to subtract this epsilon psi n, and then this is positive. So if this is very large, it will cross. If it's smaller, then it will be within the margin. All right? So that's the trick. But then I need to modify my objective. This part of the objective is to maximize the margin, because margin is 1 over w. If I minimize this, then I maximize the margin because of the 1 over thing. But I also want to draw this red line, possibly nonlinear red line, in a way that these violations are minimized. So I have dual objective. I want to minimize these violations, draw it in such a way, and I want to maximize my margin. So how do I do that? Dual objectives, I mentioned it passingly when I was discussing optimization. You do a weighted sum combination. And this is exactly what we do. We add the two objectives, and the weight is C. The other one has a weight of 1. The second objective has a weight of C, right? This is a weighted sum combination for multi-objective optimization. So my objective is then minimize this subject to these constraints. All right? Clear? So when I do this, then I can write the Lagrangian directly by writing the objective, and then these are all inequality constraints, so the Lagrange multipliers for the inequality constraints. And also there is another set of constraints, the positivity constraints for the X's. So I write them also minus these, C less than equal to minus C less than equal to 0, which means size greater than equal to 0. So essentially these I turn to the canonical form of less than equal to 0, and then an and mu n are my Lagrange multipliers for these inequalities. There are no equality constraints here. So what do I have then? If I write the Lagrangian, the constraints themselves are these, right? This is the canonical form. This is the, is a greater than equal to 0. Actually, in optimization, we were always converting to less than equal to 0. You can do that trivially. And that brings the minus sign here as well. And then the Lagrange multipliers, because these are inequality constraints, they have to be non-negative, right? When the constraints are equality constraints, Lagrange multipliers can be anything. But when they are inequality constraints, they have to be non-negative. Remember? No? You do, right? That's very fundamental. And then these are the complementary slackness conditions. I multiply the Lagrange multipliers with respective inequality constraints, and they have to be 0, which tells me either this is 0 or that is 0. That means either the constraint is active or my Lagrange multiplier is positive. So the same with the second set of constraints. All right? You see, I'm talking about support vectors. This is machine learning. And then you will be excused if you think, oh, this is an optimization course. But it is optimization. It's at the heart of it, right? Once you define what you want formally, you end up with an optimization problem. That's usually almost always the case with the machine learning and deep learning as well. Because there's no other way that we know, right? So how are you going to achieve your objective once you formalize it? You can use logic formulations, but that's a different pathway. So actually, I want to go through this, in a bit more detail because I realized I haven't done the dual of this. How do you get the dual? Because we were getting the dual and work with the dual usually. So the dual is the same as before, and then we end up with box constraints. So the difference is, in the previous case, the dual was the same, dual problem, A's are the same. We have the kernel, we have the labels, in this case T's, and then previously we had the same constraint, the an, yn becomes, tn becomes 0 as the sum. But then in the previous case we only had the Lagrange multipliers in the dual case an's being positive. So with this case, interestingly, the only thing that changes, funnily enough, after all this talk, is after all these slack variables, etc., you do the primal, which we have defined in the previous page, and you do all this, trade-off variable C and all that stuff. And when you write the dual, the only thing changes is this additional inequality, upper bound on the dual Lagrange multipliers. So when you read it from outside without knowing any optimization, you think, oh, this is almost the same thing. You just add an upper bound C, but it comes from a long way where it comes from. And where does it come from? And then you have the solution like this, but this is the same. The only thing is the margin now, when you take the sum, you need to just only take into account the set of indices of data points that are between 0 and C. All others are ignored when you make the sum, and which is very similar again in structure to the previous case where things were separable. As I say, I think it's a good idea to drive this a little bit, and I have already written the starting point. So this is what we have. This is the Lagrange multiplier for the. Let's write this somewhere. Maybe make it a bit bigger. So this is the Lagrangian Lagrange function for non-separable case. Case with slack variables psi n greater than or equal to 0, right? And those are handling the points that are possibly violating the margins, right? And then these are the these are the constraints themselves. So these are the constraints. Maybe different color. Constraints. This row is the Lagrange multipliers. They need to be non-negative because they are corresponding to inequality constraints, and then these are the complementary slackness condition. Slackness. But we don't have the now. I haven't written the whole KKTs, right? This is just part of the KKTs. The KKTs also I need to now take the derivative with respect to the decision variables, and those are these, right? So those are actually in this case, we have not, we have also the psi here as the decision variable. And psi, right? Actually, A is there too, but we need to also add psi to the mix. the slack variables. So then I need to write del L over del W equals 0, which will give me, if you take the derivative, also I know that y equals this, right? We have this, this is the discriminant function. That's what we are trying to find. Once we know W and B, then we are done. So when I take the derivative, this will become W and minus, so y has a W, so it will be sum of over n, a n, t n, phi n of x. So that's phi of xn. Phi of xn, right? So this is y of x. Okay, so this is equal to 0, therefore I get the W, that's the same as before. And then when I take the derivative with respect to B, it's even simpler because B is inside here, everything else zeroes out. When I take the derivative with respect to the B, so I only have sum of n, a n, t n equals 0, but that's the first part of my box condition. And then the last one, different from previously, I have now the derivative with respect to psi n, for each of them. When I take that derivative, w's cancel out. I get a c here minus, I get a c here. One of them I'm taking with respect to psi n, so this, when I take the derivative, only one remains here, c times 1, minus this one is here, so this will be also giving one of them to me, multiplied by an, so this will be the corresponding n here, right? How do I highlight this? Maybe, you know, this is n, okay? And then what do I have? Also, I have 1 here coming from minus mu n equals 0. What that means, an equals c minus mu n. But I also know that mu n is right? Is non-negative. C is positive. So an is then, we know we end up with an less than or equal to c. Right? But an was also less than or equal to 0 because this is the same as this. Greater than or equal to 0. I ended up with an less than or equal to c because I subtract mu n out of that. So that's the second part. So these two then are my so-called box conditions. Right? And if I substitute the W back in, if I substitute the an, tn sum equals 0, and you see this whole, all of this sum zeroes out, and then I also substitute this one, maybe another color for this, sorry. If I substitute this one into the L, so to get the dual, let me write it here. To get the dual substitute orange things. So 1, 2, and 3 orange into Lagrangian. So they zero out a lot of things. This is zeroing out a lot of the terms. This is zeroing out a lot of the terms. W equals this. You put it in. Sum of an multiplied by 1 remains, but sign becomes positive. So then the dual Lagrangian becomes sum of an minus W times W. So you get the rest of the expression that we had in the slide. Lagrangian gives me, maybe I just write it here, so gives the dual Lagrangian. And that is in terms of the A's, right? That's in the slides. Okay? I refer to the specific slides then for that one. Yeah, so that's the nice derivation. Actually, this is the extended derivation with the xi's in. The one without the xi's, when things are separable, non-linearly separable or linearly separable. Each case, in the linear case, you don't have a phi of x, but you just have x, then it's wx plus b. In the non-linearly separable case, which is hard to actually know, then it would be then, w phi of x plus b, the same discriminant function, but you don't have to talk about the size because you create the largest margin and nothing violates the margin. And in real life, you do one version of the soft margin SVM, as we have done. There are other variants. There is the mu SVM. There's another version of handling the violations. But in the interest of time and not to go into all these technical details, I am just covering the soft margin one. Just know that there are other ways of, almost equivalent ways of handling the violations like this. The main idea is the same. Right? So then the dual is this, when you substitute the W and W transpose, 1/2 was in the beginning. So it gives you the dual like this. And then the, maximize, minimize, the same dual story as we have done before. And then these are the box constraints. Any questions on this? All right, you see, this is also, you can see it as an exercise of doing a nice, dual of a Lagrangian and dual of a convex optimization problem. Remember, the SVM is a quadratic problem. Because it's a quadratic problem with convex constraints, linear constraints, actually, in this case, the constraints are linear. In phi of x, actually, yeah, these constraints are not that linear, now that I think about it. Because of y of x here, but still the constraints are convex. It's a quadratic program, convex optimization, convex objective, convex constraints. Therefore, we have no gap, no duality gap, strong duality holds. Therefore, solving the dual gives you the same result as solving the primal. And as I'm saying, the dual, almost always people solve the dual because it gives an easier solution. The dual formulation is much simpler than the original primal formulation. So you define the problem and go to the dual version because it's easier. End of story. We always want to solve the easier problem, right? It also saves computational time. All right, so quantifying classification performance, this is a lot of common sense stuff. How do we measure the performance? When we do the training test and test set, or when we do the cross-validation. In regression, you just look at the error, right? It could be the mean square error, absolute error, or root mean square error. They're almost the same story, right? You kind of use your test set, test values, actual values as the test values, and then predicted values that based on your training of the training set, and then you do the square or some square error, or you take the mean, or you take the root mean, right? Then you get the RMS and so on. So you do the regression. That's you have already done, right? With the regression in the workshop as well. So I should warn you that there are cases where root mean squared does not tell much. So if I want to, for example, compare these two images, right, noisy version and not noisy version, I can, of course, convert them to a vector and do a mean square error type of calculation. But that's not a classification problem. That's just comparing the two. Degradation, for example, this is a lot used for, this is quite important when you compress the images, right, JPEGs and so on. Image compression or video compression. So this is the image of Lena, very famous. Anyone knows this? Anyone done image processing or the story? Anyway, so this is a very nice image because it has a lot of high frequency parts and plane parts. So when you compress this image or do something with this image, if you want to check how close you are to the original image, as I said, when the metrics, objective metrics don't work, what you do, you just look at the picture, right? It's subjective. So you may have a very good RMSE score, but your algorithm may mess up the image in a very bad way. You see, RMSE doesn't tell you the whole story. So people have been using, just like MNIST dataset being now the benchmark, people have been using Lena image for forever in image processing to compare the algorithms, and then getting a subjective idea of how the after the algorithm image works, or maybe you want to do denoising, so there is noise, your algorithm cleans it up, then you want to see how it compares to the ground truth, which is the original image. There's a lot of fun story about this image and so on, but I don't have the time, and if you want, you can Google it, right? Just to tell you, sometimes in audio as well, when you do, MP3s, audio compression, whether it sounds good or not, and for which bitrate will it sound good or not, right? So all that stuff is subjective because it's for the human ears. You can have a perfectly nice mean square error, but it may sound horrible to the eye, ear, and it destroys the song. What's the point? So there's a lot of subjectivity sometimes when you deal with the image and audio data that are tied up to human systems, right? But in a more general sense, this is I've put some nice images here that really summarize the whole story. So if you are doing, for example, a classification, a binary classification in this case, so the true condition will be then the real positive and negative, and then you predict with your classifier whether it's really positive or not. And then if it's positive and you're predicting it positive, congratulations, it's going to rain tomorrow and it's raining tomorrow, then your prediction has found the correct one. That will be the true positive. Or it's not going to rain tomorrow and you predicted it correctly, that will be the true negative. But then things get messy. Ideally, we want it to be all diagonal, and we don't want to make mistakes, but you start to make mistakes when the actual thing is negative, but you predicted positive, that is a false positive, and the other one is the false negative, right? It didn't rain, you predicted rain, or vice versa, and they may have different costs, right? I mean, the cost of having an umbrella, or the cost of the city traffic being crashed because you predicted wrongly. So that's actually the whole story. Where does the ground truth come in? As we have done in our workshops, sometimes you have it, sometimes you don't. And when you don't have it, you use your data set to separate it into a test set, and then use the test set values as the ground truth to do the comparisons, classification comparisons. This is also interesting. So if you want to find the real relevant elements, true positives, and then your algorithm gives you the circle. So the job is actually the squaring the circle. Ideally, what you want is this, but in reality, you get some of them, but then you also get some false positives, and then these are the true negatives because your algorithm is imperfect. It doesn't give you the rectangle, but it gives you the circle, right? So that's another way of looking at the same thing. Yet another way of looking at the same thing is like this. So you have true positive, true negative, separating. So this would be the false negative, this would be the false positive, and then that would be my matrix, right? True positive, true negative, false positive. And then that is the same. Another thing that people use a lot is this receiver operating characteristics, ROC curve, plotting the true positive against false positive at various parameter settings. So this is, you're changing the model parameter, maybe one of them, and for each model parameter, you are somewhere in this curve. Ideally, you want 0 false positive, and you want 100% true positive, right? That's the ideal, but you never get to the ideal. You get some curve, hopefully closer to this. As your curve goes away from it, then your algorithm is not that good, obviously. And if you change the parameter of your algorithm, you are somewhere on this curve, right? There is always some trade-off. If you increase some parameter, you may get more true positive, but your false positive also increases, or vice versa. This happens a lot for anomaly detection, for example, security. If you want to catch all the spam emails, there is a trivial solution. You can classify everything as spam, then you will catch all the spam images, but you will have tons of false positives, right? Or vice versa. On the other hand, you don't classify as anything as spam, then you will miss all the spams, but then you will have 0 false positive. And then everything is in between. So that's kind of a nice thing. What people seem to use these days is, this curve, I knew this before, they also take the integral of this curve. As I said, the ideal case is when you are here, that means the curve has the maximum full square, as a full square, it would be like this, then it would be 1. Any curve that deviates from it will be less than 1, right? This would be half, this would be less than half. As I said, instead of looking at the parameter, but the whole parametric range of your algorithm, this area is telling you how good your model is. So if your model is very nice, then you're here, you get a 1. If your model is horrible, you get a 0, because there's nothing underneath the curve. If your model is in the middle, you get a half. So if you map this whole performance to a single number, then the area under this curve is what people seem to use. It's a bit oversimplification, of course, because you map the whole thing, whole picture to a single number by looking at the area underneath the curve. So, and then these are the definitions of precision, recall, F-score. You know, again, this is the same simple 4-quadrant confusion matrix. Or here as well, the y-axis is this is actual, this is predicted, this is the tilted version, transposed version of this matrix, because predicted is in the x-axis. Here the target is in the column. Yeah, that's the same. Actual is in the column. Model, which is making the predictions, is in the rows. So you have the quadrants as the true positive, because it's really positive and you predict positive, and then the true negative and false negative and false positive. I don't know. I think this is why did they write true positive here? It's a good question, right? Maybe I should delete this picture because it gives the wrong impression. Like, does it match? Yeah, it does match. Okay, let's keep it, right? So let's keep it because it matches the table, but the table is more meaningful here a bit. Otherwise, the predict, yeah, like it's just, this is the positive and then positive, negative, positive, negative. That's, by the way, this is so much ingrained that when you use sklearn, it doesn't give you the what they mean. So you need to kind of know this. So, you know, you were getting the table, confusion matrix. I gave it like, you need to know this is positive, positive, negative, negative. The ordering is kind of a convention here. So if it's positive, positive, I'm good. If these A, B, C, D are the fundamental 4 things, what I want is A and D to be as large as possible, and C and B to be 0, right? Not 0 mistakes if possible. But precision is actually A over A plus B. That's the positive predictive value. That's called precision, or positive predictive value, or precision, proportion of positive cases that are correctly identified. This is really a nice summary definitions. And then negative predictive value, people don't care that much usually about identifying the negative cases, mostly focus on the positive cases. But your application may vary, therefore precision is the named one. Then there is a recall or sensitivity, the proportion of actual positive cases which are correctly identified. So that recall will be then the sensitivity, which is A over A plus C here, right? And then this is the other definition. And the accuracy is then this true positive, true negative out of the total. This is kind of giving you how many mistakes you make. The total is in the denominator, and true parts, the column, the diagonals are added up. So that would be then the A plus D divided by everything, right? Again, a way of combining things, you know, because there's precision, there's recall, there's accuracy. People use a lot the F1 score, which takes the harmonic mean of precision and recall. You know, the geometric mean is A plus B over 2, than the regular mean. The harmonic mean is this. That's the definition of harmonic mean, 1 over divided by 2, and then taking 1 over again, which is this. So that's the harmonic mean of precision and recall. That gives you the F1 score. So there is a lot of more discussion on these. But once you know precision, recall, F1, accuracy, and then the confusion matrix, I think that's it. Also this ROC curve and area underneath, these are the main things that people care about and when you are evaluating your classifiers. All of this stuff is directly relevant to neural networks as well when you do classification with neural networks. So this is broadly applicable, right? And the same with the when you do the regression, of course, with the neural networks, you also do mean square error as your objective because the task is the same. Only tool changes. I mean, people keep asking me, what is important, what is not important for the final exam and so on. What should I know? Because I cover a lot of topics. I tried to, this year, to put them, these learning objectives, what you should know about at the end of each slide set, right? So this should give you kind of an idea. You should really know a little bit of this, and then the examples we did, and then I highlighted which examples are more informative, which questions are more about, you should be able to solve them and so on, right? So this should be also giving you some guidance. I was hoping. Yeah, let me know if it's useful. All right, so should we give a 10-minute break? 5 past, we start with the neural networks, and then, the fun part.
So here, for this question,
Right.
this one,
Yeah.
yeah, you said we want to turn it to a dual optimization problem. Is that what you?
Yes. The dual is there.
How do you mean by substitute them back into the original?
Yeah.
function?
Well, when we do the dual, we take the derivatives with respect to the primal decision variables. Yeah.
Yeah, I think.
And then with respect to the primal decision variables, and we substitute them back. Remember those slides
Yeah,
in the
because
optimization?
actually, for example, if it's about x, we want to find the x to
Lambda.
minimize the original function, and then put it back.
And that's what we are exactly doing here. We are minimizing with respect to these 3 things, though, not one thing.
So we need to.
We get rid of them and then end up with a single.
Put all these back. This
Yeah, and then actually that cleans up a lot because an equals c minus a lot of the stuff in the most of the stuff in that original Lagrangian, they zero out. You get rid of many of the terms. You just substitute w in an, and you end up with the dual.
Back, and then we find the
The
one
dual.
maximize the.
Yeah, exactly.
All right.
Yep. And subject to the dual as also the box constraints. The box constraints remain. Right?
Yeah.
So it is a very standard, the same dual thing we did.
Okay.
It's the same story.
This one, you know how, this is your linear separator,
discriminant,
and then
yeah.
you have your margin here. In this case, your margin is here.
Yeah.
What
yeah.
about where's
Margin is
up
with
here,
respect to the closest one.
Yeah, so you say the green ones are the support vectors. So
Yeah,
the ones
yeah.
that lie on the this one here.
No, that's what I meant. Like green ones are support vectors, and they don't necessarily have to be next to the boundary. They can be also far away.
Oh.
Maybe there is also undrawn boundary here. I need to.
Okay, and then that undrawn boundary is kind of like.
But
the
it
margin.
doesn't have to be. They come directly from the solving the optimization problem.
Yeah.
That gives you the optimization solution. There is no visual process to duplicate it.
Awesome.
So it gives you the support vectors.
Because
Those are the points for which their Lagrange multipliers A's are positive. End of story.
Because I can visualize here, I can see you're maximizing this margin here, but I don't know how to visualize when I.
Yeah, it is
try
not.
to
It's
draw.
not. It's not. Yeah, it's not like that. This is the result, not the.
Okay.
Yeah, this is the result.
Okay.
And also, I don't know whether I took this picture. Maybe there is another boundary here or not. I don't know.
Okay.
So, or it could be in the infinite, and then that's the closest one.
Yeah.
So it's this is the visualization of the results. So you trust the math, you solve the math, and then it gives you the picture.
Because in the workshop, it has the same. It
Yeah,
did
yeah,
the
it
same
has-
thing, but I didn't understand where the margin is.
Yeah, I don't know. I don't know either. To be honest, sometimes it's hard to interpret, but that's what the problem gives you. And maybe there is a boundary at the infinite. Maybe it goes through the infinity.
Okay.
But I shouldn't say that because I don't know.
Yeah,
It's a bit of there's math, then people talk about math. I think the main thing is the math, and then you program it, and it gives you the result.
Okay.
Then you can talk about it forever, but that's pretty much just to make ourselves happy, because it gives you the result. If you have written correctly the rule and the primal and solved the optimization problem, that's the result.
Okay.
So I don't know. Like maybe I should dig deeper. It's a good question. Yeah, I'll check it. If I find it, I'll tell.
Yeah, sure. Thank you.
What do you mean by support vector?
Those are the points that are those green points.
Yeah, but what
It means those are the points for which the Lagrange multipliers are positive. That's the definition. That's why it's called support vector machine, because it's the boundary is y is defined by those sum of an. Only the an's that are positive are playing a range. The support
Oh,
vectors.
yes.
So that's why they are supporting
it's
the
about
boundary.
active non-active.
Yeah, and then they are supporting the boundary.
Yes.
Hello.
I have a question about the basis function,
Okay. Which basis function?
the plausible basis function. This one.
Oh, okay. Yeah, these are the k x zeros for these, and these are the
Gaussian, this is for
these are one-dimensional versions.
So these two are not connected.
No, these are kind of they are kind of connected,
So
but
this is saying this is for polynomial, but this basis function is not this one, right? Because
because
we-
we say like for the polynomial kernel.
this is the polynomial kernel, and this is a picture of the polynomial kernel in one dimension. Correct, with respect to zero, x to zero. That's good. That's the thing. The basis functions are the well, you have these are the Gaussian bases, right?
yeah, but I think these two are not irrelevant.
Yes, like for this polynomial basis, you can think it as this is for this one is x, and this one is x squared, and the next one is.
Yeah.
Yeah,
But for this one, we couldn't conduct it. With
Yeah, but when you write it here, like that's a very good point. Polynomial kernel, you see there is this nth degree polynomial which will have these elements.
yes,
but for
even
example, can I understand this as y equals 0?
Yeah, y is 0. Yeah,
So if you substitute y equals 0 here,
then it will get this.
It doesn't make sense.
like if you
Yeah.
make it 0.
No, this is for the RBF. When y is 0.
No.
For
Is it-
this one,
yeah,
okay.
yeah.
So when you have y
Polynomial.
equals 0,
Yeah, it doesn't make sense. So we're thinking this graph is irrelevant to this one, and also irrelevant to this one, because this basis function definitely not.
this is from Bishop. Like
Yeah. We read the book.
But I-
It didn't explain very well.
it didn't.
It's explained a little, but didn't explain too much.
No, that's a good question.
Yeah, so we're
Let me-
thinking these two graphs are irrelevant because of basis function. Definitely not that.
Yeah, but then I think the Gaussian basis, you get the. Yeah, I wanted to put some visualization. That's the issue. So you can actually I mean, if you just if you treat them as basis functions, they are basis functions. We agree on that.
Yeah.
So this is kx0. That is also.
which is irrelevant to here, because they cannot be the basis function for this kernel.
Ah.
Yeah.
Why? This is the polynomial kernel's expression.
Yeah. So because for this one, the basis function is x squared x cube. If we do like times x times y, then it would be xy plus x squared times y squared plus x cube times y cube. If y equals 0, then everything equals 0.
Well, not for the Gaussian.
No, for the polynomial.
Depends on how you define the polynomial. They defined it here like this.
These two are not irrelevant.
Okay, but for the Gaussian, you will be able to write it this way.
For the Gaussian, if you make y equals 0, then
Let me check this. Okay, that's a good point. Maybe I need to put more explanation here. So that's a good point. Yeah, let's agree on that. I mean, this is the just general kernel expressions, right? And then this graph gives the basis functions, and then this kx zeros. But then I need to write the expression maybe here in another slide, or maybe separate them.
Yes.
So I will do that. Thanks for notifying. Yeah, I'll do that. Yeah, it's on my mind. Well, I need to start. Yeah. So, but that's good. So I will add that. I will actually update many of the slides. Some of the things we discussed yesterday is also on my to-do list. I will update those earlier slides. So towards the end, we will have a new set of slides, and I'll announce everyone to download the newest versions.
Okay.
Because they will have more explanations and corrections, all of them. Okay. All these are very useful. Thank you.
Thank you.
All right. All right, let's continue. Now the modern part of the lecture, but we've been, as you noticed, we've been building up, right? So I covered optimization, but optimization is also at the title of the subject. The reason is you can use optimization for engineering, as you know, right? It's heavily used these days. So that is an objective in itself. A secondary objective of covering optimization in the beginning is, as you have seen multiple times, it is the foundation for machine learning and deep learning. We haven't seen the deep learning part, but it is a foundation for machine learning. Most of the machine learning problems, as you have seen, we have defined them as optimization problems in various ways. Then, if this was a subject I covered 15, 20 years ago, this whole machine learning, support vector machines would be the main players. People fell in love with support vector machines in the 90s until the turn of the century because they were beautifully convex. Everybody loves convex optimization because it's very well defined. You can derive things, write your KKTs. It's not messy. It's elegant and simple. Although it's nonlinear because it's convex, which is what matters in optimization, continuous optimization. So people liked it, and then they were also quite successful in solving some of the canonical classification problems, right? And then that went for a long while, and that was the dormant time for neural networks. The neural networks went back to sleep for a while. The history of neural networks is really interesting. So first people got very excited about it. The model is inspired by how the neurons work. When in the 50s people were discovering the bodies, all this DNA and other stuff, and then people were observing the neurons, they are firing. That inspired the whole, the perceptron thing, and people created these early models. Then the history is I've put a link, I think, to history that is somewhere in the links at some point, maybe in the introduction slides. So then someone who likes logic more than these connectionist models didn't like these neural networks. Then he showed something that we will discuss soon, and then it went out of favor, made a big comeback in 80s. People made a big fuss about them. Of course, the computers weren't that powerful in 80s. And then the training of the neural networks, people couldn't find very good algorithms. So it went back to dormant. Support vector machines come up. And then the classical machine learning support vector machines and other stuff, now they are dormant. And then the deep learning neural networks made a big comeback. Who knows what will happen next? So it's a bit sinusoidal with these things, what becomes popular and not. Usually popularity is dictated by the performance. If the tools solve certain long-standing problems, then it becomes suddenly very popular. So now, long history I mentioned, the feed-forward neural networks or deep feed-forward networks or multi-layer perceptrons, they are all the same thing. We will see, or small variances. But the whole story is this blue line. The goal of a feed-forward network is to approximate some function. That's the end of the story, right? So that means what? Like this is, I tried to put it to a very executive summary here. Y equals fx maps an input to an output. Y could be a set, then you're doing classification. Y could be 0, 1, then you're doing binary classification. Or Y could be a value, then you're doing regression, right? And X is your input. So maybe Y is a real valued function, then you're doing function approximation with the real values. So the problems are the same. We are talking about the same set of problems, regression, classification, binary, non-binary. And then the whole idea is, as I said, feed-forward network defines a mapping. Let's say Y equals G of X, and then you have the parameters theta. These are the weights and other things in the feed-forward network. Learns from a data set, XY pairs, as we have done before, and learns the parameters, thetas, the theta vector, such that this gx theta approximates f of x. All right, that's the end of it. It's very simple, deceptively simple, right? So this should be very clear to everyone, I think, and it will be, I think, once you also play with them. What are the advantages and disadvantages? These are provable universal function approximators. There's a very classic paper that establishes that. You can theoretically show that you can approximate a very, very large class of functions with neural networks. A single hidden layer neural network like this. This is the input layer, this is the hidden layer, and this is the output layer, right? And there could be a single dot at the output layer, or you have multiple outputs. And the single dot could be doing a classification or regression, depending on what you choose. But simple neural network, which was the classical one, this is the classical one, this is sufficient to approximate a very, very large class of functions. That's good. Can handle data very well? Yes. I mean, we will see. You give me the data, then I use the data to come up with this neural network, and the neural network approximates the function underlying the data doing this, y equals f of x. And why is it important? Engineering problems and their solutions are full of functions, right? So when you are approximating these functions, you are coming up with a solution. That's very powerful. There are also disadvantages, right? No method is perfect. So the training data set is mapped to parameters automatically through optimization, through a training scheme. And then model selection is tricky. There is a bit of art, as I was saying, aspect to it. And then even more importantly and then bothersome part, and this is the part which makes a lot of people hate this stuff. And I'm always advocating balanced views, not liking or... You shouldn't fall in love with a method, or you should not hate a method. Keep a cool head, right? I've seen more than enough people doing that in my career, especially in academia, that the guy falls in love with certain method, then anything else ignores it, or vice versa, hates a method and never listens the good sides of it. That's a bit dumb, to be honest. Here, what people hate is it's a black box method. As I said, it gives you a solution, but it doesn't tell you how it solved the problem, right? That's a bit, not very good. And actually, it's a hot topic these days in deep learning. The model, explanatory models, it's a research topic. People want these deep learning networks to work, but also they want to understand why they work when they provide a solution to a problem. All right. The difference between the classical and the deep learning neural network is exactly this. In the classical case, it was always one layer. Because it was universal approximator, people said, okay, that's good enough. Why should I need another layer? This is a universal approximator. But these days, I will come to this. You have multiple layers, and they work very well because of the modern training schemes as well. So there is actually really nice neural network zoo link here, and then this poster, I squished it to fit it here. I encourage you to go and click, and you will see there are so many versions of neural networks. I will not be able to cover all of it. One of the most important ones, and the appropriate beginning, is the feed-forward ones, like the ones they are depicted here on the top, right? And then I will do CNN and a little bit, and I will do the RNN LSTM. I will probably mention the autoencoders a little bit, and then I will leave it there. I cannot, make you visit the whole zoo, cover it here, but once you know these fundamentals, you can catch up. Okay, so now we want to come up with this model. How does this happen? What are these thetas? So for that, we can go to Bishop and classical stuff. We don't need anything else, and then that's duplicated in the deep learning book as well, if you notice. So if we come up with a functional model for a single hidden layer, and the multi-hidden layer is just an extension, straightforward extension of that. You just add more hidden layers. So then when you add more hidden layers, now you're suddenly doing deep learning, and it's very popular and deep. And then, this single hidden layer model has been around forever, since 90s, so it's quite old. Well, it's the same thing. The fundamentals are the same. I mean, there are differences, but I will highlight. Okay? So remember the linear machine learning models for regression and classification. We have this model. You have the basis functions. We were just discussing with some people. You have this nonlinear maps, and then you do a weighted sum of them to get a linear model. So it is linear in the basis functions of these transforms. It's not linear in X. That's why they are called linear models. But you can also have phi of x equals x. Then it's the simplest version. Then phi of x is being identity function. Then you have the simple linear model that is also linear in X. And then you can put also an f in front of it, right? I will define everything. Now I think I've defined everything in the slide, right? So the neural networks also use these basis functions that follow the same form. So that is a linear function, nonlinear function of a linear combination of the inputs, where coefficients are the adaptive parameters. So the coefficients here are my theta. If you put them together, that's my parameter vector theta that I mentioned in the previous slide. So we need to find the coefficients. So let's define things first. So we have this A. If we bring structure, it's easier to handle. So if we do this linear combination and plus a bias term, then we can write this A equals W, so X. So this is essentially a matrix multiplication, right? And then with some addition. So these quantities are called the activations, the A, the linear combination, and then you have a nonlinear activation function that acts upon that, right? So the output of the basis functions are then called the hidden units. So input to hidden layer is then looking like this. I do a linear combination, and then I pass it to a nonlinear activation function. So that's actually the picture. So I have the inputs, there's a bias. Actually, you can get rid of the bias by incorporating it to the terms. So then you take the inputs, you do multiply them with these W's or omegas. That you can represent as a matrix multiplication, and then that creates the input to the hidden units. You can have multiple hidden units. You can have up to infinite hidden units, and then that gives me the input to the hidden units. And then I take the hidden units, the hidden layer to the output. Z is then after I do the linear multiplication, matrix multiplication, I pass it through the activation function. So in the first layer, I take the input vector elements, and then I do a linear product as described to get the A, and then I pass it through a mostly nonlinear activation function, h of x, h of A, to get the Z. And then Z's become the input to the next layer. So it's a very layered system. So you feed forward, so you go layer by layer to the forward. So then you take the Z's and then do the same thing. So you do a linear combination of the Z's for each AK, and then you pass the AK through some nonlinearity to get the Y outputs. So the output, then these become the output units, right? So this is the input, this is the hidden layer, and then the activation function in the hidden layer, and this is the output. So the activation function in the output layer, they are dictated by what we want as an output from the network. Input is dictated by my X, obviously. Hidden layers is something I can play with. I can put one or more. I can choose my activation functions for each layer. I can do all that stuff, but in the output, I should actually choose my activation function based on what I want as an output. If I want to do regression, actually, you put a linear activation function, which is y of x is yk equals ak. There is no nonlinearity at that level. Then this will give you a real value. If I want a binary classification, what people classically do, what people do even today and have been done forever, is putting a sigmoid. Then you get a 0 or 1. That will give you a classification, right? And then if you want to do multi-class, then you choose a softmax. That will give you a multi-class classification. So the whole equation for the one hidden layer is done. This is, as I said, classical neural network. Y is taking X, do a linear combination, put a bias as well. The bias is not terribly important. Pass it through the nonlinear activation function H. Then that becomes the input to the second layer. H's are linearly combined. Again, there could be a second bias term. And then that is passed through the output activation function. Output activation function, which can be also linear, but it could be also sigmoid or something else, or tangent H. You have choices, right? So that's the equation. Is this clear? This is kind of the feed-forward explanation. And if you have more layers, this will be things will be like onion, right? More things inside the equation. More hidden layers. It's also going straight forward from left to right, or top to bottom, bottom to, wherever. So you are not doing any loops here. Everything going step by step. Everything goes from first layer to the second layer to the third layer. You don't get the cross graph. Perceptron to MLP, and then multi-layer multi-layer perceptron, which is a neural network. Essentially, they call it neural network. And then if you have many layers, then it's a deep neural network. That's almost a buzzword. Let's call everything a neural network and save us the pain. So the perceptron was this 50s thing that I mentioned. So people did, in that case, simply a linear combination and then a simple step function as the output nonlinearity. So that was a classifier, right? Linear combination and the step function. So single hidden layer was the most commonly one used in practice until the deep learning. So that was most of the last century. These, and I mentioned, they are universal, provable, mathematically provable universal function approximators. But knowing the existence is different from finding the weights. So the theorem tells you, oh, this can approximate any function. And then you say to the mathematician, oh, great, thank you for this fantastic result. But could you tell me how I'm going to find those weights? And the mathematician tells you, I have no idea. So, and then you say, well, that's great. That makes a great paper. Well, what am I going to do with that? And actually, people didn't know what to do with it for a long while. And then they used it, but single layers were not that powerful. We will discuss this. Before going, so that's the finding the weights is at the heart of the discussion if you want to do engineering. And I should tell you one thing. We are almost all electrical engineers in this classroom. Right? I'll tell you a secret. The computer scientists working on this deep learning do excellent engineering. And that's a big surprise, right? They do better engineering than many electrical engineers. All this stuff is done purely in software, may not have physical models, but the way they put those layers together, and when I say layers, not these layers, but the components together, is excellent engineering. And they work with real data, so they get real results. That's why it's popular. There's a reason why this is a buzzword. They are doing excellent engineering in firms like Google and Amazon and Facebook in this domain, abstract domain. So don't get the wrong impression. They are just programming stuff away. There's excellent engineering going on here underneath the whole deep learning stuff. I'll cover the basics, but some of that impressive results come from that engineering. So let's start from the simple. So this is actually historically interesting, the XOR problem. How am I going to find the weights? I would like to motivate that. So this is a problem that is very simple. The data set is 4 points. And I would like to say, let's use a neural network to implement an XOR function. You know the XOR function, right? So that's this function, the gate and the truth table, right? It's a very fundamental function in logic. So that goes back to this discussion and the fight in 70s. So when people came up with the neural networks, logic guys said, oh, can your neural network learn this logic function? And then it turns out for a version of the neural network, it couldn't. And they said, your neural network is useless. And that was like, it killed the neural network research for 10 years. So then they asked that guy who wrote that book and gave this example saying, you know, are you happy now? You killed the neural networks and now they are deep learning and you cost us 10 years. And I think he was saying, oh, I didn't do anything and so on. But like he was after his own funding. So if x1 is this, x2 is this, all the data is 4 points. This is really funny, right? So you have all the combinations here, input combinations, that's it. The goal is to find theta such that we have this function. And we can use mean square error as the cost function to minimize, which kind of makes sense. Let's start with this. And if we do a linear function, that was the thing. So if you do a linear function and then do a perceptron, a step function at the output of this, then we can find the parameters theta, and then in this case it would be omega 1, omega 2b, by minimizing the convex MSE cost. So actually when you do this, you get the wrong answer. So you get the parameters that gives you the wrong answer, and this is the story. Okay, here's the history thing. So it showed that it's impossible for such linear models, even with a step function at the output, to learn the XOR function, and that's what killed it. So people got disappointed. So this is my interpretation. So it turns out this result was only limited to the perceptrons. And that's what I tell you. You can quote me on this. Never fully believe when experts tell you something is impossible. Believe it when they say it's possible, that's good. But if they tell you it's impossible, don't believe it. I have actually encountered some impossibility theorems. It turns out if you change the output of the theorem by epsilon, it's possible. And practically that epsilon doesn't matter. So that impossibility result it looks very nice on paper, it's totally irrelevant. So it was a case of that. And it turns out if I do a 2-layer network with a hidden layer, I can perfectly solve this problem. So, and that's exactly the structure that we have, right? So you have 2 inputs, one hidden layer with 2 hidden layer nodes, and 1 output. That's a special case of the equation that I wrote down, f2, f1x, and then they are written in this form. We have the W matrix. In this case, it's very simple. Then the second one have the hidden activation and so on. So if the both layers were linear, they would collapse to a single linear layer. So the key here is this nonlinearities that are in the middle. I would like to emphasize that. So we need a nonlinearity in our activation functions. Otherwise, I will show in the next question, you can have many layers, they all collapse to a single linear layer. So it's meaningless. So the thing becomes meaningful because you do some linear thing and then pass it through some nonlinearity, even the simplest nonlinearity, then you do a linear thing and pass it to the nonlinearity. So it is a nonlinear mapping, iterative nonlinear mapping. That's very important. And the popular choice for the activation functions, I will discuss it in further, is the ReLU, rectifier linear unit. And it is the simplest possible function you can think of as a nonlinearity. It is just 0 when x is negative, and when x is positive, it's a simple line. So therefore, this equation becomes, when you plug it in, the first layer is linear combination, passing through linear combination at the hidden layer, pass it through the ReLU, then that would be the max of 0 this, plus the second layer B and the second layer thing, and then Y is just we use a linear output for this case because I'm not putting another nonlinearity here. Right? It could have been done with the nonlinearity as well. I could have put a sigmoid as well, right? But I'm just keeping it simple here. Right? So show that actually the next question, I would like to do the next question first because this is very important to drive the point. Show that a multi-layer neural network with only linear layers is equivalent to a single layer network model that is linear regardless of the number of layers. So let's do this because as I say, it really drives the point and it makes you hopefully not forget it. So let's write this down. And we can use a mathematical induction. We show it for one layer. So if we have one layer, proof by induction. So show for one layer, then you get what? Like we have W1 x1 plus b, right? That's linear. So then assume it holds for k layers. Holds for k layers. Then we have wk x plus bk. Then show k plus 1 collapses to a linear single layer. Therefore, because it holds for 1 and holds for k plus 1 collapses, then it holds for any k. So you can repeat this as many times as you like, they all collapse. Why does it happen? It's very simple math. So when I write wk plus 1, one more layer, and take the output of the previous layer as the input, A plus bk plus 1, I can multiply, rearrange the terms. The terms, what do I have? Then this is a matrix multiplication, so the two matrices multiply, wk plus 1 wk x, right? Plus, so this is matrix multiplication, these are two matrices. And this is a vector, this is a vector as well, because the layer output is a vector. It doesn't have to be scalar. Right? And then plus, then this multiplies this, wk plus 1 times bk, plus bk plus 1. So this gives me a vector, this gives me a vector, these vectors are summed up. But, if I define this as w tilde, and this as b tilde, then this is nothing but w tilde x plus b tilde, but this is linear. So you can repeat this as many times, you end up with linear. So if you don't put a nonlinearity to the middles, activation functions, you are doing a linear model. So you are back to 1969, and you cannot even find XOR, right? And then that's the story. What is this? I was going to say also, how does ReLU look like? ReLU looks like this. So ReLU is if x, so you got, if it's negative, it's 0. So it's a saturation function, and it's y equals x when it's positive, right? This is the simplest possible nonlinearity you can think of. You just zero out the negative values. Yeah, interesting. And it works very well. I'll come to that, why it works very well. Actually, that's the most popular activation function these days. People were doing tangent, hyperbolic tangent before in the classical case, but ReLU is the activation function for hidden layers these days, for deep learning. Apparently it's sufficient. Even this much nonlinearity is sufficient. So you don't need an exotic nonlinearity to make things work. Okay, so we have shown that we need then, I wanted to drive this important point that we need some nonlinearity in activation functions. So we put our nonlinearity to our hidden layer and satisfied that condition. And now we put also the output layer, and in the output layer we didn't put any activation function, so we put a linear activation function in practice. Then you get this result, y equals x, activation function wise. And it turns out I can actually choose the matrix and the bias and the omegas and the W matrix of the equation that comes from this neural network. This is the neural network. This is the equation that it implements. This is the feed-forward equation, right? It takes x as an input, gives you the output. And now I'm going to just give you the result. And you can actually write this result and verify for any x input combination for XOR, these parameters give you the right result. So we can verify this result, and then we have a solution. Neural network can solve the XOR problem, okay? Even with a single hidden layer and simple nonlinearity like ReLU. But then I didn't tell you where the solution comes from, right? It's a by hand design. How are we going to compute these parameters for real world problems? We will discuss this not soon, but next, I think maybe I should say next year, because it's the next slide. I think when I wrote it, maybe I was putting something in the middle, but now it's the next, okay? What happened? No, next slide. Training neural networks. Not next year, this year, immediately. I should start it. Okay, any questions until now? So now you know what the neural networks are, what do they, at least feed-forward ones, what do they do? You need hidden layer, at least one or more, then it becomes deep, and then you need the activation functions, otherwise there's no point of adding new deep layers. And if you give them, if you have the right parameters, you get any function you like, that's fantastic, but how am I going to get these parameters? I need to train the neural network, I need to do supervised learning. So this is a straightforward supervised learning question, because I have the data set that consists of X and Y's, inputs and outputs, and I need to train my neural network with X and Y's to get the supervised learning. Actually, you can use neural networks also for unsupervised learning, and I will have slides for that next week. But right now we are doing supervised learning. So training a neural network means learning its weights using the training data set, right? That's the main sentence. And surprise, surprise, this is formulated as an optimization problem. All right? How do I get this? I solve an optimization problem. Optimization problem gives me the parameters to the best possible capabilities. The largest difference between linear models and neural networks is that these embedded nonlinearities that I mentioned, that I cannot get rid of, and I need them, they make the loss functions non-convex. So convex optimization is good. That was people fell in love, as I was saying, in support vector machines, partly because of that. But then these loss functions, when you have a neural network, they become non-convex. Convex optimization fundamentals apply, right? Because locally things are convex. You find the local minimum, then you jump and find the local minimum, and so on. So you do all kinds of, you still do gradient descent. So you start somewhere, do a gradient descent, find the local minimum, maybe you jump, you do it again, and so on, right? Gradient descent variants are still the most popular methods for training different kinds of neural networks in deep learning as well. So before going to the gradient descent, which we already know though, we should look at the cost functions first. You need to talk about the cost functions. What am I optimizing? I need to know my cost function. That is the question first. And in order to discuss the cost functions, I need to give you some basics of information theory. What I realized when I created this subject is, you know, I've been trying to teach you something nice, right? So that was the goal. And I worked it backwards. I did a backwards propagation, like a neural network. So I want to give them these capabilities. What do I need? They need to do something by hand, so by themselves. So that created the workshops. Good. But for that, you need to know Python and the sklearn and Keras. So they come automatically. It's not my fault. So then, in order to teach the neural networks, I need to teach a little bit of the basics of the classical machine learning. And for the classical machine learning, you need the optimization. For optimization, you need the vectors and differentials and calculus and derivatives and the linear algebra. It's not my fault, guys. Like, I mean, if you want to learn this stuff, you need to learn the whole stack. It's the reality. Like, I mean, people actually blast me saying, you tried to squeeze too much in. But if you want the real end result, yeah, it's a marathon. It's a pyramid. It's a pyramid that you need to build upon. So I have to unfortunately go information theory basics and entropy. But here is a good summary. I learned my lesson in the beginning, not doing a review of linear algebra, so I'm going to do the info theory in a kind of from the first principles. I start with a random variable, refreshing your memory. What is a random variable? It's a function that assigns a real number to an outcome in the space of a random experiment, right? this is, this is good to revisit. As you revisit, you get a better understanding. So this is the space of outcomes, S, set of outcomes, and this is one outcome. And then the experiments are random, like throwing a dice, right? The action of throwing a dice is this randomly getting a point out of this space S, experiment space S. And the physical fact that once you throw the dice and one side comes up is that experiment, right? And then the one side comes up, I use a function to map that to a real value. And that is where these dots come into the picture. So the dots that I paint on the top of the dice, they map the outcome of the experiment, the fact that that side is up, I map it to a number. And that is actually a real random variable. This is actually, I'm happy with this definition. So then, what does entropy mean? Entropy of a random variable like this tells us how many bits are required to quantify the uncertainty of the random variable. So that's all entropy is about. This is a clean definition. So entropy of this random variable x then is the sum over the action possibilities p of x log 1 over p of x. So that's the definition. And if you have an entropy of a fair dice, uniform probability, then that is log 2, 6, because this is 1 over 6. There are 6 possibilities, they cancel out. Then 1 over 6 comes to the 6, 1 over 6 becomes 6. This is log 2 if you want bits, so that's log 2, 6, okay? So then you get this many bits to describe that uncertainty. And then if the dice is, if you're a bad gambler and then the dice is loaded, it always comes 6 for you, then there is no uncertainty. Then the probability that it comes 6 is 1, so you get log 2, 1 is 0, no uncertainty, therefore 0 entropy. All right? So that's the story. You know this much, right? Yes. Okay, excellent. So now you remember. It's good to remember. Kullback-Leibler divergence. Then we come to the second thing that's a lot used also in the objective functions of the machine learning is Kullback-Leibler divergence. It is a way to compare two distributions. They could be like this, the PMFs, discrete distributions, or they could be continuous PDFs, right? This definition is, it's widely used. It is a divergence because it's not a distance metric. It's not symmetric. It doesn't satisfy the triangle inequality. dpq is not same as dqp. So you find the divergence from one of the, you need to choose the first distribution you like, and then you find the divergence of the second with respect to one. It is just this. So you have this expression that you take the expectation over px, and then you take the log px over qx, and that log, because of the division, you can write it in the long form like this. So that's Kullback-Leibler divergence. Just functionally, you know this one? Or is it the first time? So functionally, if you want to compare two distributions, what are you going to do? Go to thing is KL. All right, that's this function. It's a very valuable function. If I have two distributions, how am I going to know how different they are from each other? I use the KL distance, divergence. Yeah, people sometimes say distance. It's an abuse of saying it's not a distance as we discussed in a mathematical sense. So we will use KL, and then the third thing is the cross entropy. So the cross entropy is between two probability distributions. We have the entropies for a single probability distribution, cross entropies between the two. It is defined as such. Again, I'm just giving the definition here, HPQ. So that is minus P, taking the expectation over P, and then log of QX, right? Actually, as you can see, these things are so similar to each other, and as you can expect, we can combine this definition with the other two definitions we just seen, the KL divergence and the entropy of P or entropy of Q I can also write. And if I substitute the terms, it turns out this cross entropy is nothing but KL divergence plus the entropy of P. You just substitute the, mechanically, algebraically, you can substitute them, right? So that's the cross entropy. And then now I'm coming to the business. Back to the business, so I've defined entropy, KL divergence. KL is really, really used a lot, so that's, I should maybe tell Margareta to teach it in the probability. And then the cross entropy, you must have seen it as well. Maybe I should tell her, ask her, beg her to teach that stuff or mention it at least, because if you hear it twice, it's better than hearing it once. What do? When we train the model neural networks, surprise, surprise, we are using again the maximum likelihood estimation of their parameters, right? So all that maximum likelihood stuff we did, it immediately applies. Because at the end of the day, neural network has a set of parameters, all these theta is all these W's and B's and so on, coming from the layer weights. And I want to know those, and then I can actually put it very much immediately to a maximum likelihood estimation framework. Now these next three slides, connect everything together in a circular way. It's really turns out to be interesting. So let's start from the beginning. We have set of M examples, right? And then let's make this IID assumption, because I'm adopting a probabilistic point of view of the world. There is an underlying probability distribution, and data comes from this distribution in an IID way. That is a simplification, obviously. That's a mental construct. Real data doesn't have to be like that. But this mental construct buys me a lot of mileage. So that is the P data X. This is the ideal probability distribution that I will never ever know in practice, but I can approximate, right, or use it as a mental construct. So the goal is to find the theta ML, maximum likelihood theta, which by maximizing the probability of the model, the joint probability of the model, right? So this is an equivalent to doing the X given theta, as we were doing Bayesian version just a few slides ago or a couple of weeks ago. So if I make this assumption, then I can write this in terms of the individual data points. Because they are IID, I can multiply these probabilities. They are independent. And then this maximization product problem, I can make my life easier by taking the logarithm. So then I do the log likelihood, and then that will turn the product, which is a bit bothersome, to sum, because when I take the derivative, sum is better than product. So I get the sum log P model Xi, and I want to still maximize this, right? So this is actually the same as taking the and then this is the maximum likelihood. What you don't see here is actually maximum likelihood doesn't put any prior to the probabilities of the thetas, right? They are all uniform. Therefore, they are uniform probability 1 over m for each case. So you sum over m. Actually, you have an expectation over the x. You can write it as an expectation and log P model x theta as such. So as I mentioned, we adopt this probabilistic point of view. We only know the data set. Therefore, the expectation over true distribution, which we don't know and may never know, because we only have the data, can only be approximated in practice. And then I do this expectation out of that because of this. So because this is the best I can do. So now we want to interpret this. So one way to interpret this maximum likelihood estimation of neural network parameters is minimizing the dissimilarity between data distribution and the model distribution. So that's what I'm trying to do, right? So I want to create a neural network model that approximates the data as much as possible, right? That's the approximation business that I said in the beginning. Y equals f of x, and my y equals g of x theta, which is the neural network representation. They should come together. So that's, I can now use the KL divergence, because these are two distributions. I want to bring the two distributions together, and I want to minimize this KL divergence between these two distributions. So that is exactly the DKL, P hat data and P model, my model. So I want to minimize this divergence. And that I can write from the definition of KL. A couple of slides ago, I can write it this way. But there is an interesting thing going on here. The first term is fixed for a given data set. Actually, from the given data set, I can derive the probability distribution of that data set. We have done this, right? You can use Gaussian mixture models, for example. So you can make a nice estimation of this. So this is given. There is nothing to optimize here. So everything is done. Minimizing this is minimizing this minus second term. Minimizing minus second term is same as maximizing the second term. And practically, we have this with the data set. We have the sum over the data set log this. So expectation over the model, or sum over the data and log P model. You see, we have come to the same point. So we have done the maximum likelihood, and we can start from, I want to minimize the KL divergence between my own model and the real data, and then that represents the function. But because this is fixed, if I write the DKL and minimize, I end up with the same thing. So I'm trying to achieve the same thing. I'm just starting from different ways and end up in different places. So actually there's even one more connection. Minimizing this KL divergence also corresponds to exactly to minimizing the cross entropy between these distributions. Why? Because cross entropy, remember, is KL divergence plus the fixed HP. But HP is constant like the first term in the KL here. So therefore doesn't have an effect in the optimization. So it turns out if I try to minimize my cross entropy, that is equivalent to minimizing the DKL, but that is what I was doing just a second ago, and that is the same as what I was doing in the previous slide, that is the maximum likelihood of theta. So all three are the same thing. You see the connections? So it's like really dancing around the same objective, interpreting it in different ways. And the last one is conditional likelihood, and actually I can even tie it to the mean square error. There's one more connection. So remember, in supervised learning, maximum likelihood estimation aims to maximize the conditional probability, py of pi y given x and theta, in order to predict y given x, right? So we had this. So if I want to maximize this probability, that is same as minimizing this cost. Therefore, I put a minus sign here. So these minus signs are kind of, because it's a cost, I minimize it, so there is a minus, then this becomes max. If you are careful, you will see we switch between minimizing cost and minimizing distance and maximizing the likelihood, and the appropriate minus signs pop up in the right places. So if I write it this way, and now I will make an assumption to make a connection, right? So assume that this probability is Gaussian, which doesn't have to be, but then if I put the Gaussian as a prior here, and then P is y given x is then a Gaussian distribution, normal distribution, where the mean is what I want, and there is some variance, right? So this is an assumption I put on top. Then we can write it down as the sum of log this is, if I write the log of the Gaussian distribution, I get a lot of constant terms, but also this term. And then if I want to maximize this, there's a minus sign here, that is minimizing this. But this is also constant, that comes from our assumption. And voila, I got the cost function that minimizes the expectation with respect to y minus the f of x. This is my prediction minus the mean that I'm trying to estimate. So that is the square error. So under the Gaussian assumption, then there is also a direct relationship between the square error and the maximum likelihood estimation. So all things then tie up together. So I do maximum likelihood for finding my parameters, which is equivalent to minimizing the KL divergence between my model distribution and the data distribution, which makes sense, which is equivalent to minimizing cross entropy, and which is equivalent to, under the Gaussian assumption, the last one has an additional assumption, to the minimizing the mean square error. Is it surprising? Maybe not, because at the end of the day, I want the same thing, right? So just different ways of seeing the same thing. At the end of the day, I want to find those parameters that achieve this function approximation. This is just different ways of formulating it. Why did I have to? I have not included a single thing that you don't need. The KL is really used. Entropy is needed to define the KL. And then the cross entropy, you will say, why did you include cross entropy? The reason is cross entropy is the standard go-to-loss function for classification. For binary case, if you have a binary classification problem, the conditional distribution of the targets then follows this probability of label given x and the weights is given by this Bernoulli distribution, right? And if I want to minimize the error loss function is as we discussed, the error loss function to minimize will be then negative of the log likelihood because I want to maximize the likelihood. The maximizing the likelihood or minimizing the minus likelihood then would be this, because then I do this product and then take the log likelihood of this probability as we have done over the dataset n1 to n, and you have this expression, right? This is what I'm trying to minimize. The minus comes from, because I try to maximize log likelihood, that becomes a minus cost to minimize. This is called the cross-entropy error or cross-entropy loss. What you see here is, this is the standard way. You will see all in blog posts and everywhere in sklearn, the guidelines and handbooks. Look at this, what this is. So if I write the definition of the cross-entropy and write P equals T and 1 minus T is P is 1 minus T, Q equals Y, and 1 minus Q is 1 minus Y, and remembering info-theoretic definition of the cross-entropy, this is exactly the cross-entropy. So this the cross-entropy loss is properly named because it minimizes the maximum likelihood error, and then that is the minimizing the cross-entropy loss. So because we did this two class version, because cross-entropy loss is more general over all possible multiple classes, so it generally generalizes directly to the multi-class problems. So bottom line is, if I'm doing regression, I use the minimum mean square error, which is equivalent to using maximum likelihood estimation of my parameters. Or if I'm doing classification, I use the cross-entropy loss in my neural network as the loss function, but that is equivalent also to cross-entropy from the info-theoretic definition, and that also ties up with the maximum likelihood estimation of my parameters. And then I'm kind of covered the good amount of bases. I've covered the classification and the regression, the main two problems. So these are the loss functions to cover and discuss. All right? So it's a bit amount of stuff to absorb, but it took me a lot of time to put this together from multiple resources to give you a consistent picture. I hope the slides are kind of you should be able to follow these slides when you go back home and revise the material. Let me know if you see any gaps or suggestions for further explanation. All right. So we continue tomorrow. Thanks.